Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 31, part B. We're still talking about the gamma distribution. This is the second part of 3. Last time we derived the PDF of the gamma distribution, and I will write it again, but in terms of, so f of x equals 1 over theta to the alpha, gamma to the alpha, the gamma function, let's do x to the alpha minus 1, e to the negative x over theta. Now here we have to put the x is greater than 0, or as the book does it, either one is fine. We have 0, x, and I think they include 0 there, to infinity. But if we write it with a generic term for theta and alpha, we also have to specify that alpha is greater than 0 and theta is greater than 0. As soon as we plug in a value for alpha and theta, we don't need to include this part because they won't show up in the equation, will they? There'll be a number there, and it'll be a positive number. So let's say that theta equals 3 and alpha equals 2, then f of x would equal 1 over 3 squared gamma of 2, and we'll talk about what that equals in a minute, and then x to the 2 minus 1, which would be 1, which is x, e to the negative x over 3, and then we'd say x is greater than or equal to 0. This would be my final PDF and how you should write it. Or actually, I would hope that you would go ahead and we're about to learn that this is going to be 1 over 9 x e to the negative x over 3, x greater than or equal to 0. Gamma of alpha, we're about to find out, is equal to alpha minus 1 factorial. And alpha here is 2, so 2 minus 1 equals 1 factorial, which is 1. And don't forget that 0 factorial is also equal to 1. Okay? And so 3 squared, of course, is 9. So that's how we got this. This is what I would expect to see for an answer on a test. Okay, so we're going to continue with the gamma distribution. And last time we got to there, and I'm going to, we talked about that alpha is the shape parameter, and theta is the scale parameter. I hope you'll write that on your distribution sheet for the gamma distribution. I also hope that you'll write down the gamma function either on this sheet or on a separate, on your formula sheet, one of the two. So what you need to know is you need to be able to recognize this function because it's going to be required in order for you to solve or do some proofs, okay? So pattern recognition is a very powerful tool for proofs, especially in statistics when we're talking about continuous distributions or even discrete distributions. This pattern recognition is extremely important. So this requires integration by parts. I want to remind you that the integral of u dv is equal to uv. If this is, I'm going to say negative infinity to positive infinity, so negative infinity to positive infinity, because I want you to remember that you have to evaluate that u times v, then minus the integral, and you switch. If I have u here, I need du. If I have dv, I need v. So v du. And again, negative infinity to infinity. So I should have zoomed in more. So integral of u dv equals uv, that's supposed to be a v, evaluated from the limits. I put negative infinity to positive infinity, but whatever, it may not be defined on all of that. So from the lower limit to the upper limit, and then we have the integral from v du from the lower limit to the upper limit. Okay, so let's review how we do this. We are going to set, we're wanting to integrate the gamma function. And so we're wanting to set something u to something that goes away eventually. All right, so that's the strategy. And remember that this is going to be, t is a positive number, so it just has to be greater than 0. It doesn't have to be greater than 1, but in general, if it is greater than 1, we can set this here, u to y raised to the t minus 1. When we take the derivative, we have a constant out front and t minus 2, and we can keep doing that until we get to y to the 0, right? So that means that we have some finite number of integrations by parts to get rid of this term. I can integrate this by itself easily, but here this causes a problem, okay? So until I get rid of this term here, I struggle to integrate this, okay? So u is set to something that's going to diminish and try to go away as fast as possible. And dv is set to something that you can integrate, but it may not go away, all right? So that's one strategy for this. I'm not saying it's the only one, but it is one strategy for integration by parts. So here I take the integral of e to the negative y, so I take the coefficient, I divide by that coefficient. When I integrate, 1 over negative 1 is simply negative 1, so I end up with a negative out here. Now, as I wrote before, let me write again, it is integral of u dv equals uv evaluated from, let's say, a to b, if this is a to b, minus the integral of v du. So uv is right here, and my gamma function is from 0 to infinity. So again, you need to look for integrals that go from 0 to infinity, or try to get them to be from 0 to infinity a certain way. You have to be careful with that. We have some techniques, but you have to follow the rules. And so this is a negative y to the t minus 1 e to the negative y from 0 to infinity plus, and now we do the reason I do it this way is I take these, and then I take what's on the bottom times each other, and then it's easy for me to remember. It's uv, the ones without any derivatives, those times each other, minus what's on the bottom multiplied times each other, v du, with an integral. So I can pull the t minus 1 out to the front, and then since I'm subtracting here, but it's already a negative, it becomes a positive, which I like. And then I've got y to the t minus 2 e to the negative y dy. And here, the t is out here, so I do have a y here. And so I have to be careful whenever I'm plugging in infinity. So 0, I don't have to worry about too much unless I'm taking 0 over 0, but that's not the case. So I can rewrite this as this here. And if I plug in 0 for that, so I've got a negative, so when I subtract, I got a positive. I plug in 0 for y, I get 0 over e to the 0. E to the 0 is 1, so I get 0 over 1, which is 0, so that's what this is. I don't need L'Hopital's for this. But when I plug in infinity here, remember for L'Hopital's, we have to make it, we sometimes have to trick it into being a fraction with y on the top, or x if you're dealing with x, and y on the bottom. So this negative exponent easily lets me take e to the y to the bottom. And if I plug in infinity, I've got negative infinity divided by e to the infinity is infinity. So I've got infinity over infinity. Infinity over infinity is indeterminate. So is 0 over 0. And so is 0 times infinity. These are all indeterminate forms. Let's see, infinity divided by 0 is also indeterminate. But 0 over infinity is 0. Why? Because this is the same as 0 times 1 over infinity, which is equal to 0 times 0, which is equal to 0. So that shouldn't be indeterminate. I hope I'm not wrong on that, but it seems pretty logical to me. Okay, and so this is going to be infinity over infinity. I'm going to have to use L'Hopital's rule to evaluate the first expression there, but I have 0 in the second. I'm going to go ahead and evaluate what I can. I still have my integral over here, And so with L'Hopital, I take the derivative of the top, which is going to give me, it's negative here, but this is positive. So negative t minus 1, y to the t minus 2. I missed that, sorry. So don't forget to subtract 1 from your exponent there. And then I end up with e to the y, the derivative of that is still e to the y. So it stays the same. It's going to stay constant. And what I've pointed out here is that eventually this becomes a constant after I take t minus 1 derivative. So I could keep taking L'Hopital's derivatives over and over and over again. Eventually, this is going to go to a constant. A derivative of a constant is 0. I have that divided by e to the infinity, so 0 times 1 over infinity. Again, that's going to be 0 times 1 over infinity, which is 0 times 0, which is 0. So this eventually goes to 0. I didn't prove it. We would use induction to prove this, and it would be quite tedious to do so, but we could use induction to do that. Okay, so now I've shown you that this whole term here, the first term, uv, and oh my gosh, that's messy. So uv here, this goes to 0. But you can't just say that. If you just say that to me, then I will be forced to take off points because you have to show me. And in the case of something like this, you can say exactly what I've said here, that this eventually, you take I've been specific. You take t minus 1 derivatives, as long as t is an integer, then a positive integer, then that becomes a constant, 1, and you've got these constants out front because t is a constant with respect to y. So you've got some constant divided by something, and when you take the derivative of a constant, you end up with 0, but actually you stop, right? When you get a constant, you have the constant divided by, that's right. So we don't have 0 over 0. We'd have negative t minus 1, t minus 2, t minus 3, until we got to 2 and 1. So we'd have negative t minus 1 factorial over e to the y, and that would be negative t minus 1 factorial, whatever that is, over infinity, which is going to be 0. So I hope you followed that. If not, rewind, ignore what I said about 0 times, we don't take that last derivative. Once we don't have a variable, we don't take the derivative again. L'Hopital's doesn't, oh, actually it does, right? So once we have just y left, then we will, the next derivative will give us a 1 times this constant. So that will be this constant here, divided by this, which didn't change. And this is a constant divided by infinity is still going to be 0. All right. Sorry to take extra time for that, but I just want to make sure that it's clear that you follow that. If you have questions, please ask me. I'm happy to help you out with that. Okay, so that means that we end up with this, and I want to now point out that this here is the gamma function for t minus 1, because I can write t minus 2 is equal to t minus 1, parentheses, minus 1. So we need the form. We need to look at the form up here. If I clean this up again. If we look at the form, we have y something raised to the something minus 1. So this t minus 1, whatever it is, and then e to the negative y. So we look down here in this mess that I've done, and we have, in this integral, we have t minus 1 out here, and so this becomes t minus 1 minus 1. We still have e to the y, negative y, and we still have 0 to infinity. So this is, instead of gamma to the t, this is going to be gamma to the t minus 1, and we had t minus 1 out in the front. And again, using induction, we can prove that gamma t is equal to t minus 1 factorial for all t in the natural numbers. And so here are the properties that you need to know about the gamma function. First, because gamma 1 is 1, because gamma, if first we would actually want to prove this first, which I haven't proved it, but I've shown that that would be true if we used induction. We could prove it. And so I'm going to use this to show that gamma of 1 equals 1 minus 1 factorial, which is 0 factorial, which is 1. And then we did show this one. So I first did this to prove this is what we would have proved. I didn't prove it. And then we used that to prove this. Okay? So once we've proven, when we've proven this one, we can then use induction from that to prove the next one. And then from that, we can directly prove the first. All right. So we will stop there for this video. Please don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. Update your either your distributions with this gamma function or a separate formula sheet, or however you want to handle that. That's up to you, but I would make sure that those properties are somewhere where you can find them quickly. If you have questions, again, come to virtual office hours or email me a picture of your work and the problem, and I'll be glad to help you through email. I hope you will take care of